Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. And in this video, we're going to step into polynomial and rational functions. This is assuming that you've had Algebra 2. However, it is not assuming that you've had college algebra. So there is a significant amount of review in this chapter. However, it's going to be somewhat high level or, well, appropriately leveled, at least for a college algebra course. We're going to start with a discussion about quadratic functions. So let's go ahead and remind ourselves about a few things that quadratic functions have that we need to be aware of. So this definition is a pretty beefy definition. I'm just going to read it out here. The graph of a quadratic function is a curve called a parabola, and that should be very familiar to you. It has an extreme point called the vertex, and I will go ahead and just showcase this. You should all know from your experience in mathematics thus far that that is the shape of a parabola. And the extreme point that I'm mentioning, which is called the vertex, is this type of extreme point. It's either the highest high or the lowest low on the graph. And if the parabola opens up like the one that I've graphed here, then the vertex represents the lowest point on the graph, or what we call the minimum value. That will become more important as you move forward in mathematics. You need to know the minimum and maximum values. On the other hand, if the parabola was upside down, it would be the vertex that would be a maximum value. In either case, that vertex is what we call a turning point on the graph. Although, to be honest with you, that's not something I hold my students to knowing, but that is true, that it is a turning point on the graph. The graph is also symmetric about a vertical line, and I'll showcase that here, called the axis of symmetry. And that should be somewhat obvious from this graph, even though my graph is not perfect here. It should actually be more like maybe this. So maybe I should clean that up a little bit. Still, that's terrible, but whatever. So that red vertical line is called the axis of symmetry. Remember, vertical lines have equations of the form x equals some number. So in this case, because x is positive, that might be an x equals 3 or something like that. So be very aware of that. So always the axis of symmetry for a parabola that opens up or down will have an equation of x equals something. As with all functions, the x-intercepts, which this one currently does not have, represent the zeros or the roots of the quadratic function. Zeros or roots are just fancy names for x-intercepts. Well, actually, they're more involved than that. So if there's a mathematician watching this, they don't yell at me. I'll just let you know. I do realize that zeros and roots are slightly different than just x-intercepts. So anyhow, that's kind of the basic language we all have had from the past. And now we're going to move forward and still recall some extra stuff here. Now, normally I try to break my videos up into little subsections. However, that first subsection was a single page. I just didn't feel like breaking it up into its separate video. So I'll continue into this subsection as well. Understanding how the graphs of parabolas are related to their quadratic functions. First, we need to know the form of a quadratic function. There are actually two of them. In fact, all polynomials have the same two forms. They have what's called a general form and another one we'll talk about a little bit later. The general form of a quadratic function is f of x equals ax squared plus bx plus c. Probably the easiest way to remember that you're dealing with the general form of a polynomial is that there are no parentheses or grouping symbols involved. So it's completely distributed out. That is the general form. A, B, and C in this case would be real numbers, so non-complex, they're complex numbers, but they don't have imaginary parts. And A has to be non-zero. The reason for that is because if A were actually equal to 0, well, it would then be a line. It'd be just bx plus c, which would not be a quadratic. So let's go ahead and just do a quick example. If you want, pause the video and try this out. Write this quadratic function in general form. All right, so to do so, you're going to go ahead and take this quadratic function here. You'll just distribute things out. So this is a no-brainer, right? You just go ahead and multiply out this binomial. Remember, it's binomial squared. So that's going to be 9x squared minus 6x plus 1. Then you distribute the negative 2/3 through. So let's see, negative 2/3 times 9. Let's see, that's a negative 3, negative 6x squared. Negative 2/3 times a negative 6 is a positive 4x. Double check my mathematics here. 6 divided by 3 is 2 times 2 is 4. Yep, that's right. And finally, a negative 2/3. Now, you don't want to leave it like this. Obviously, you have a little bit of grouping you can do here, or like terms. This constant is the same type of term as that constant back there. The first one, 3, is just 9/3 minus 2/3 would be 7/3. And so in the end, we get this beautiful quadratic function written in general form. Let's just finish that out. Now, as you can see, it actually looks, they both look very complex. I think a lot of people find that they look fairly complicated. They both have their uses. So the first form, the form that they handed it to us in, this guy right here, is a very powerful form that we'll discuss in a little bit. However, applications tend to be given in general form. Or when you build your own application, you tend to build it to be in general form. So again, when asked to write a quadratic function in general form, just multiply it out, get rid of the grouping symbols. As with any topic in mathematics that you kind of open up with, for example, the first section in any given chapter, you have a lot of definitions and a lot of theorems to kind of help you with the rest of the material in that chapter. There's no difference here. We have this initial theorem that tells us that if the lead coefficient A is positive in the general form, then the parabola will open up. If it's negative, well, the parabola opens downward. And you should recall that, honestly, from your Algebra 2 course. The question here is, does the graph of the quadratic function in our previous example open upwards or downwards? So if we hop back, you could see that our quadratic function here has a lead coefficient, the A value here, and I probably shouldn't use red, I should use green. The value of A here is less than 0. So if we were to graph this, the parabola that represents this quadratic function would open downward. And so that's the answer to that question. Rather than writing it, I just highlight it there, but you get the idea. So whenever you're handed a quadratic function, you're looking at that lead coefficient. If it's positive, you know that the parabola, that is the graph of that quadratic function, opens up. If it's negative, it opens down. Our next theorem here, actually, we're going to prove, and this is because you're in college algebra, so we're going to try to sneak in as many proofs as we possibly can. The axis of symmetry for a parabola is x equals negative b over 2a. Now, I have to be very honest with you. I am not a huge fan of memorizing formulas, so I do not personally use this formula in my classroom or that often in my lectures if I do a video lecture, because I like a general, good, strong understanding of what things are rather than a memorized understanding, not even understanding, just a rote memorization of what things are. So anyhow, this is just letting us know that if we had a parabola, we could compute the axis of symmetry by considering the general form of that parabola, or the general form of the quadratic function that parabola represents, so ax squared plus bx plus c. And I'm telling you in this theorem that the equation for that axis of symmetry must be x equals negative b over 2a. Now, why is that true? Well, it comes from the fact that we have to use the quadratic formula at some point when we're working with quadratics. So to start our proof, we'll go ahead and consider the quadratic function f of x equals ax squared plus bx plus c. Now, if you're going to search for, let's say, its x-intercepts, you're going to set that equal to 0. That is, if f has roots or zeros, then they can be found by solving f of x equals 0. I'd say if here because it turns out that there are some parabolas that just don't have roots or zeros that are real. For example, if I zoom out here, if the x-axis for this parabola that you see over here, if that was here, you see that the parabola that is would never strike the x-axis. So that parabola would have no x-intercepts. That also means that it doesn't have any zeros or roots that are real numbers. However, it will always have complex valued roots. So you don't need to know exactly what I mean by that, other than the fact that if you set the quadratic function here equal to 0, then you would use the quadratic formula, and if your parabola did not strike the x-axis, you would get imaginary solutions to that. So you would get basically no real solutions. But there's still something very important about those solutions. And let's go ahead and use that idea right now. So we'll set our function equal to 0. Notice that's a quadratic function, quadratic equation, and you can use the quadratic formula to go ahead and solve for x. So that would give us that x is equal to a big old fraction. You know the quadratic formula from years of use. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And that's how most students memorize that. However, this can be written in a slightly different format. You could split that fraction into two pieces. The negative b over 2a part and the plus or minus square root of b squared minus 4ac over 2a part. So I just split that fraction into two pieces. Something critically important to show you here. If there was an x-intercept for this quadratic function, let's just pretend there was. And so rather than me graphing a new quadratic function, I'll go ahead and just say, suppose that we had a couple x-intercepts. I'll even zoom in here and I'll mark them. Here's one and here's one. Notice that they're symmetrically placed away from this axis of symmetry. In other words, they're the same step away from that red vertical line. So this point is whatever the red line is plus a wiggle, and this point right here is whatever the red line is minus the same wiggle. Focus in on that. One of them is at red line plus wiggle, one of them is at red line minus wiggle. Now let's go back to the statement right here. This is where the red line is, and we're going to wiggle to the right and to the left by this certain amount. So that red line is actually at the center between those two intercepts, which is at negative b over 2a. Now, to write this rigorously, I should probably be a little clear about this. Thus, the intercepts, if they exist, are symmetric about the line x equals negative b over 2a. Now, you might wonder, well, wait a second, what if the intercepts don't exist? It still is symmetric about negative b over 2a. The parabola, that is symmetric about negative b over 2a. So I'm not going to go into that detail, but at least we get this far with the proof, and I'm pretty happy with that. That's pretty solid for a proof. So that shows us that the axis of symmetry is actually at x equals negative b over 2a. So let's go ahead and state the axis of symmetry for the parabola in our very first example. Well, here's that very first example. And if you look at our quadratic function written in general form, we have that a is equal to negative 6, b is equal to 4, and nobody really cares about c right now because honestly, all I'm worried about is where is the axis of symmetry. So if a is negative 6, b is 4, let's go ahead and answer that question. Let's see, the axis of symmetry would be at negative b over 2a. So subbing in these values, let's see, that's going to be a negative 4 over twice the negative 6. That's a negative 4 over a negative 12, which is 1/3. So that's where our axis of symmetry is in that very first example. X equals 1/3. Now we get into the second form of a polynomial, or in this case of a quadratic function, but this actually applies to polynomials as well. It's called the standard form, and this is when you do have grouping symbols involved. The standard form of a quadratic function, which is also, by the way, called the vertex form. I don't use that language too much, but it is actually probably a better language for it, is the quadratic function of the form f of x equals a times the quantity x minus h and quantity squared plus k, where h and k, h comma k, is the vertex of the parabola. The same rule applies as before. If a is positive, the parabola opens up. If a is negative, it opens down. And again, you should recall this from your Algebra 2 class. Now, I don't have a very specific example showcasing this yet, but let's just take the very first example that we dealt with in this video, which is f of x is equal to that 3 minus 2/3 times the quantity 3x minus 1 and quantity squared. It's very important that you know the lead coefficient, or not the lead coefficient, I shouldn't say it that way, but the coefficient of x must be 1 to be able to talk about this vertex form. It's critically important, in fact. So if I wanted to know what the vertex is based off this form, notice that there are grouping symbols here, so this is probably in vertex form. The first thing I'm going to do is rewrite it by rearranging using the commutativity property of addition. So negative 2/3 times the group 3x minus 1 and quantity squared, and then plus 3. At least I have it in that order right there. And you can see, if I zoom out, that it sort of matches our vertex form. Sort of. The issue here is that 3 hanging out in front of the x. The way you can fix that is by factoring that 3 out of the out of the squaring function. I'll show you how that's done. It's kind of uncommon that you have to do this. So this is a higher level example than you would probably normally see, but I'm going to start very simply. I'm going to change my grouping symbol only because I think that it's going to lose people if I do too much at once. So I just changed my grouping symbol. Nothing really radical there. The next thing I'm going to do is factor off of the x and the constant there, 3. I want the coefficient of x to be a 1, so I don't want it to be a 3, so I'm going to factor a 3 off of both x and that 1. Everything on the inside of the parentheses, essentially. Let me showcase that in a different color. So I've factored off a 3. Remember, factoring is the same thing as division. So 3x divided by 3 is just x, and a negative 1 divided by 3 is a negative 1/3. You could double check that. If you multiply that 3 back through, you should get 3x minus 1. So I haven't really changed anything. I've just done a little bit of factoring. Now I can apply that square using the properties of laws of exponents here. You should remember the product of bases raised to a power is the product of those bases being raised to their own powers. So a times b to the n is a to the nth times b to the nth. I really don't like saying that in language because it is very hard for people to follow that. In fact, if somebody told me that, I would probably also kind of quirk my head a little bit and say, what did you say? But basically that just means that you can apply this power to both items, both factors inside the exponent there. So let's go ahead and do this. It's going to be a negative 2 over 3 times 3 squared times x minus 1/3 being squared, and then plus 3. And of course, now you can simplify this. That's 9 times 2/3, or in other words, let's see, 3 goes into 9. 3 times 2 is 6. X minus 1/3 squared plus 3. Now this is a lot of work just to get down to say, you know what? The vertex is the first highlighted item here, the first highlighted term is h, and the second highlighted term is k. It has to be x minus, by the way. Another way you can think about that is whatever turns this factor into 0 is what h should be. Okay, that's another way to think about it. So let's see. So our vertex here is going to be at 1/3, comma 3. There you go. So that's a way you can do it. It's kind of because I just grabbed the very first example, it's a little bit robust, but still you should be able to follow that. Now let's see what you've probably done in the past. So in the past, you've been given a function like this, which is given to you in general form. This is a quadratic function in general form, and you've been asked to rewrite it in standard form. It depends on your instructor and what they want, but for me, I don't really force students a lot to write things in standard form. It's a skill that you need to have, but there are other ways I like to graph parabolas than to rewrite them in standard form. But I'll still showcase the skill here because you're going to need it for your future courses. So to write this in standard form, you have to use completing the square. Now, being able to complete the square is a strong prerequisite for this course. That is an Algebra 1 skill, so I'm very much assuming that you already know how to do that. However, I do slightly review it here at a higher level. If I lose you, you should search or Google or YouTube, if that's a verb, a video on how to complete the square. So let's go ahead and do it here, though. So I have my function, f of x. It is originally written as 3x squared minus 5x minus 1. Now I'm going to do a slight modification. I'm going to factor a 3 off the first two terms. So if I factor, remember factoring is division. So I'm dividing the first term by 3 and the second term by 3. It's the first two terms because you want to get all the stuff with x's into a parenthesis and all the stuff without x's out, keep that outside the parenthesis. It is 3 that we're choosing to factor out because I need the lead coefficient of x squared, that is, to be 1. If you double check my mathematics there and distribute that 3 back through, you'll see that is actually 3x squared minus 5x. So it does work out. The next thing you need to do, and notice I've left a little bit of space in there. The next thing you need to do is add to the inside of this parentheses, and I'm going to write this in green, 1/2 of that negative 5/3 squared. I'm going to write it kind of slowly here. So I'm going to add 1/2 of that negative 5/3 squared. Now notice that green ink was not there. So I'm actually adding something to this function that wasn't originally there. If I keep it like that, if I don't modify this function, to make up for that, then I have completely changed this function. And we can't do that. We have to keep things the same. It's sort of like somebody coming in the room and saying, I have the number 3. And somebody else says, no, you don't. You have 3 minus 1. But they mean to say you have 3. They should have said you have 3 minus 1 plus 1. They need to offset that to keep the number still 3. If they subtract 1, they have to add 1 back. It's a terrible example, but you get what I'm saying, hopefully. So how do you offset that addition of that green ink? Well, if you say you subtract that green ink, you're sort of right. So if you say, well, I see I'm adding that green ink, so I better subtract that green ink. You are sort of correct if you think that's true. But it turns out that you're not just adding that green ink, you're adding 3 times that green ink. So you have to be aware of that coefficient that's hanging out front. And because of that, you need to subtract 3 times that green ink. And there you go. That's how you complete that square. And what you get in the end is 3 times x squared minus 5/3 x plus, and what is this, a negative 5 over 6 squared. A lot of people would actually multiply that out. You shouldn't. You should not multiply that out. Minus 1 minus 3 times a negative 5/6 being squared. That I will multiply out. But the stuff on the inside of these parentheses, I'm not going to, because that ends up being a perfect square trinomial. That's why we completed the square. This is going to be 3 times. I'm going to steal one of these x's right here, and I'm going to steal this number, negative 5/6. Watch what happens. So this becomes x and then a negative 5/6 and quantity squared. If you multiply this out, I promise you that will become x squared minus 5/3 x minus 5/6. So it does work out. I promise you it does. I'll leave it to you to check that. But the rest of this, you just have to do a little bit of arithmetic here. This is minus 1. Let's see. So this is minus 3 times 25/36. So I do have to do some little arithmetic. 3 goes in 36 12 times. So that's minus 25/12. So in the end, we have 3 times x minus 5 over 6 and quantity squared. Minus 12 over 12 minus another 25 over 12 is a negative 37 over 12. Not the most beautiful problem, but again, one that you should be able to do. That is that function, which they handed to us in general form. It is now written in standard form, or vertex form. And the strength of vertex form is that you can tell the vertex of the graphed parabola here is going to be 5/6, comma, negative 37/12. The strength of the vertex form is honestly that it gives you the vertex, but also you can, from this form, see that the parabola is going to open upwards. So not only do we have the vertex, which we can plot, but then we know it opens upwards. So it almost gives us the entire parabola. To find another point on that parabola, you could just plug in any value you want for x, and now you have the entire parabola. Now, I'm not going to say that that's how I normally would graph, but that's how I think most people would. I have a very special way of graphing, which I don't mind showing you, but I'm going to probably wait until I get to the graphing material. Now we're to a how-to. And again, I just need to repeat that normally if it's a new concept, I don't like giving how-tos, which are like recipes. But because this is a review concept and you have done this multiple times in the past, it is assumed that you have already been pre-exposed, so I don't mind giving you a recipe at this point. So given a graph of a quadratic function, let's suppose that you're expected to write the equation of the function in general form. So how do you do that? Well, look for the vertex. And that's just done by looking for the horizontal shift. That value is h. And the vertical shift. That value would be k, right? That's how far you've lifted it up. And we've done a review of transformations of functions, so that should be okay. You substitute those values into the function f of x equals, this business right here. I'm not going to say it out loud just because it sounds mathy when I start to do that, but there you go, you substitute it in. When you do that, you have almost the entire function. The only thing you're missing would be the letter or the variable. It's not really a variable, but the parameter a. To find that, substitute the value of any other point other than the vertex that appears on the graph of the parabola in for x and f of x, or x and y, if you want to say it that way, because f of x is just a fancy way of saying y. Once you do that, you will have some number is equal to a times some number minus some number squared plus some number, but the only thing you won't have at that point is a, so you could solve for a, and you'll be able to find out what a is. And now you have everything you need to actually write the equation in general form. Let's see how this works. So write the equation of the graphed quadratic function. And I'm going to just expand on that and say, write the equation in general form. And the reason why I want to do that is because I want to make sure that you can see the difference between the standard form and the general form. Standard form is awesome, don't get me wrong, but I would like to get to general form if I can. So let's see here. I look at the parabola and I identify the shift. Well, that's pretty easy because the vertex will tell us the shift. The vertex is at -3, 2. So that means that h is a -3 and k is 2. H is basically the distance. Where did you move the x value for the vertex? And k is where did you move the y value for the vertex? So at this point, we're almost done. The vertex form of our parabola will look like this. A, because we don't know the lead coefficient yet, times x minus the h value squared plus the k value. I'll just clean that up. That's a times the quantity x plus 3 and quantity squared plus 2. Great. So that tells us almost everything we need. Now, I still have one piece I don't know in this quadratic function. The value of a. To find that, I could take any other point on the curve and try to make it an easy point. Luckily, I've labeled one for you. I've given you the point at x equals -1, y equals 0. You could also, by the way, use the point at x equals -5, y equals 0. They'll both give you the same value for a. So there's no harm, no foul if you do that. But I'm going to choose the one I've labeled there. So we're going to let x equal -1 and y equals 0. Notice how nice the equation gets. The y value is 0, the output, and the input, x, is -1. This allows us to start to solve for a. Subtract 2 from both sides. You have 4a is equal to a -2, so therefore a must equal a -1/2. Now just go back to your original function, that one, this guy right here, and substitute in -1/2 for a. So f of x must therefore be a -1/2 times x plus 3 quantity squared plus 2. A little logic check doesn't hurt. Our parabola should be upside down because that's a negative lead coefficient. And if you look at that parabola, it sure is. That's a great, fast way to just do a logic check. And remember, I wanted the final answer in general form, which just means multiply this out. So a quick multiplication here, and I might just pause the video for this, leads to a -1/2 times the quantity x squared plus 6x plus 9 and quantity plus 2. And when you distribute the -1/2 through, you get that business. And I'll do the final simplification live here. So that's a -1/2 x squared minus 3x. And then you have a -9/2 plus 4/2 is a -5/2. And that is the general form of our function. Now you've seen this theorem before. Given a quadratic function in general form, the vertex is located at -b/2a comma f of negative b over 2a. Again, this is not one that I like to teach. I actually dislike teaching this form, mainly because it's memorizable. And so a lot of students end up rote memorizing this without understanding why it's true. So let's discuss why it's true. The proof of this actually is a really nice example of how proofs should really look in an algebra course. So here we go. We'll go ahead and start with a form of the quadratic function where we know where the vertex is, which is called the vertex form. So from that vertex form, we happen to know that the vertex is at x equals h and y equals k. That's how the vertex form works. What we want to prove is that h is equal to a negative b over 2a. Well, that's not going to be too terrible if we go ahead and multiply that out. So let's do this. I'm actually going to take that vertex form here and we'll just do that multiplication. I'll do it live because I'd like to talk my way through it. So that's a times, if you multiply out x minus h quantity squared, you'll get x squared minus 2hx plus h squared plus k. If you distribute that a through, you get ax squared minus 2ahx plus ah squared plus k. All right. I want you to focus in on this negative 2ah. That's a critical piece here because, well, it is. Okay. Now, also, you know that the general form for the quadratic function is the following. F of x equals ax squared plus bx plus c. I should note the a in both of these situations is identical. In fact, let me use a highlighter for that. This a and this a, they're the same a's. Notice the coefficient of x in our general form is b, and the coefficient of the expanded value in the standard form is negative 2ah. But those are both the coefficient of x. So those things have to be the same. They must be equal. Let me write that down. Since these both represent the same function, the coefficients of x must be the same. That is, negative 2ah must equal the coefficient of x right here, which is b. Now remember what we said about h from the get-go. We know the vertex, I'll highlight this in yellow here. We know that the vertex is at x equals h, y equals k. I'm not really concerned about the y value, to be honest with you. I want to somehow create a relationship with h. So I know the vertex is at h, and look what we have in this equality here, h. If I solve that for h, then I'll get the following. H is equal to b divided by a negative 2a, or in other words, negative b over 2a. And that is my condition. Remember, h is the x value of the vertex. And what did I just find out? H is equal to a negative b over 2a. And what did my theorem state? Given a quadratic function in general form, the vertex is located at negative b over 2a, comma something. The something is just the y value when you plug in negative b over 2a. So this other part is just the y value at negative b over 2a. So that part I don't need to worry about. I just really want to showcase that the x value has to be a negative b over 2a, and we did. That was actually kind of nice. Very smooth proof. QED, quod erat demonstratum, so it has been demonstrated. That's the end of most proofs, QED. So let's go back into another how-to. If I give you a quadratic function in general form, you should be able to find the vertex of the parabola. How do you do that? Well, you start by just identifying that a, b, and c for the general form, and you happen to know that the x value for the vertex is at negative b over 2a, and the y value is the function evaluated at negative b over 2a. That is pretty much it. And that's also sort of why I don't bother with the negative b over 2a business, or maybe I should say I don't bother with the standard form business, is because there's actually a nicer way of doing all of this. So let's step into an application here and use all the skills we've talked about thus far, and then some. So a ball is thrown into the air from the top of a building. Its height in meters above ground as a function of time in seconds, that's a lot, is given by h of t is equal to a negative 4.9 t squared plus 24t plus 8. Anyway, there's a function. It gives the height of a ball at a certain amount of time. Okay. Part A, how long does it take for that ball to reach maximum height? Now, if you think about the path of the ball as a function of time, not a function of distance, but a function of time, you're throwing it starting at a height of 8, because you're standing on top of a building, and you throw it up in the air. It comes back down. But time ticks forward after you throw it up in the air. So as you throw up in the air, it will reach a maximum, and then as time ticks forward, it'll eventually smack dab into the ground, right? And we're asking, what is that maximum point? So what is the maximum height? And that's essentially asking, what's the vertex of this parabola? And it is a parabola because it's given by a quadratic function. There are several ways of doing this. We'll do this problem using the mechanics that we introduced in this video, but then I'm going to go back through and do this a better way, in my opinion. So maximum height, that just means find the vertex. And we happen to know the value of the vertex is at negative b over 2a, and then the y value is just, well, the function evaluated, and our function actually in this case is h, evaluated at negative b over 2a. Well, a here is negative 4.9, b is 24, and c is 8. Though c is not even used. Notice that's kind of interesting. C is not even used in this formula for the vertex. Kind of interesting. So let's see. This implies that the vertex, or the maximum, I should say, is at, let's see, a negative 24 over twice a. Here's a right here. Multiply that by 2. That'd be a negative, what is it, 9.8. So obviously, when you have decimals within fractions, that means you're going to need to grab a calculator because you don't want to have decimals within fractions. And the y value is just the height at that 24 over 9.8. I didn't bother writing the negatives because they cancel. So let's go ahead and figure out what that is. I just grabbed a calculator just right next to me, and it is going to be a decimal approximation. I'm going to round to 3 decimal places. It's 2.449, comma, h of 2.449. Again, roughly. Now, think about what this point stands for right now. The input for our function is time. So I know that the maximum is reached at t equals 2.449 seconds. So after basically 4 or 5 seconds, we have a maximum height. And to find out the actual maximum height, we just plug in 2.449 into our function. And I'll go ahead and do that. And I get 37.388 meters. That's rounded. And honestly, that's too much rounding. Or maybe I should say that's too many decimal places, because we're really over accentuating the accuracy here. Most scientists would really dislike that I did that. We would probably round to 1 decimal place here, but I'm just rounding to 3 just to keep as many digits in my computation as possible. So there we go. That's how you could use that formula. What's the maximum height? Okay, well, we just answered that, 37.3, I'll just say actually 0.4 meters. And how long does it take to reach? That was 2.4 seconds. And then when will it hit the ground? That's actually a great question. When will it hit the ground? Well, the height of the ball when it hits the ground is 0. So we would need to solve h of t equals 0. We want the height to be 0. I just threw that in here because it's always nice to keep you on your toes, to kind of keep you thinking about what you should be doing. So if I set that equal to 0, that function will have a negative 4.9 t squared. I already forgot the function, plus 24t plus 8. So plus 24t plus 8 is equal to 0. I am not going to try to factor this, even if it is factorable. It's just because it has decimals within it. So I'm going to go ahead and use the quadratic formula. Let's see, a negative 24 plus or minus the square root of 24 squared minus 4 times a, which is negative 4.9, times c, which is positive 8, all over twice negative 4.9, or twice a. And remember, when you do these computations, probably the biggest mistake I'll see on something like this in a class is that people will not follow the order of operations. Do all the interior work first, right? I shouldn't have to say this, you guys are in college algebra, but make sure you clean up all that stuff that I've just highlighted first before you do everything else. Make sure that you multiply this stuff out again by itself and then bring everything together. I'll showcase a little bit of that here. Very nice cleanup. And then I'll just go ahead and say it's either at negative 24 over negative 9.8 plus or minus square root of 732.8 over 9.8. Now you might yell at me and say, wait, no. That denominator was a negative 9.8. You can't do that. What happened to the negative 9.8 downstairs? And I will say it got absorbed into the plus or minus. Right? So if you really want to see it in action, it became a minus plus. Who cares? Right? It just switches those signs. Still, you have one that loses, one that gains. And just to let you know, this is, I like this example for a couple reasons. So t will be 24 over 9.8, either minus, I'll do the minus first, either minus square root of 732.8 over 9.8, or t will be equal to, again, 24 over 9.8, I'll grab a calculator for that, plus the square root of 732.8 over, again, 9.8. Now think about that. Just think about that logically, because that's what you're going to have to do in calculus. You're going to have to think in terms of logic. So you want to get your brain ready for that. Here is our vertex. It's actually at 24 over 9.8, whatever that value was. Oh, it's 2.449. Okay. So it's at that value. Great. Awesomeness. Well, you have two choices here. Either wiggle to the left of that or wiggle to the right of that. Well, come on. You can see it has to wiggle to the right to get to this time value right there. So our winner for the time when it hits the ground is going to be that. That's a good, quick logic piece. And now I'm going to go ahead and plug that into my calculator just to showcase the value. And that is, zooming in here, approximately 5.2 seconds. So about 5.2 seconds later, it will hit the ground. Now, I did say that I would like to showcase a different way of graphing. So a lot of people will graph a function like this using negative b over 2a and f of negative b over 2a and all that fun stuff. I'm going to take advantage of the last few minutes of this video, if you're still alive and still kicking and watching this, to show you a very unique and powerful way of graphing quadratic functions given in general form. So I'm going to go back to this. It was negative 4.9 t squared. So I'm going to write this down. There was our original function. Now I'm going to give you a very natural way of thinking about how the graph of this parabola looks and how to find the vertex. You could memorize that negative b over 2a junk, because that's exactly what it is. It's just rote memorization junk. But if you have a natural understanding of what a parabola looks like, It's a U-shaped object. It's not exactly a U because it continually widens, but it looks like that, doesn't it? And because it continually widens, you know that that graph will eventually hit the y-axis. That's the critical piece, because if you think about a point on the y-axis, its input, or time value in this case, is 0. Its output is some number. So the way that I highly recommend graphing parabolas and finding vertices and all that fun stuff is the following. Ask yourself, when does the parabola hit the y-axis? Well, that is a natural easy question for you to answer at this point. It hits the y-axis when your input is 0. So you evaluate h of 0. And that is a super duper easy thing to see, because all it is this. 8. It's just that 8. So I can easily start to graph this parabola. Even though they didn't ask me to, I can at least say, I know at time 0, it's at a height of 8. Well, another thing you should note about parabolas, if they reach a height at some point, and that height is not the vertex itself, they will end up, because they're U-shaped, achieving that height again at some other time. There's a symmetric point where it becomes that height again. It's like a roller coaster where you go down this roller coaster, and at some point you're at a height of 8 feet off the ground. Eventually, when you climb back up, you'll be at 8 feet off the ground again. So again, it's a very natural question. When is our output going to be 8 again? If you're a child looking at a roller coaster, and here's the ground, and you see this, and you say, wow, they're really high right there. And you would easily notice they'd be at the same height later on. It's a natural, visual. So if you are good at natural visuals like that, then it might be okay for you to ask, when is it going to be 8 again? And that is yet another really nice question to answer, because that just means you want to know, when is the output, h of t, equal to 8? And something always happens here. Something beautiful always happens here. Notice when I set the output to be 8 and I go to solve this equation, the 8's cancel. That will always be the case. Doesn't matter what your time 0 value was. If it was 110 or pi, doesn't really matter. The fact is, when you ask the second question, it'll always lead to the following. 0 is equal to a negative 4.9 t squared plus 24t. In reality, it will always lead to, and I'm going to write this in blue below this, it'll always lead to 0 is equal to a t squared plus bt. But ignore the a's and the b's. I don't care about that. I want a natural understanding of this. Now, if you're solving this equation, notice both of those terms have a t in common. So I'll just factor that out. So I get 0 is equal to t times the quantity negative 4.9 t plus 24. So the answer to that question, when is the output equal to 8? Well, that would be at time 0, when t is equal to 0, or when this junk is equal to 0. Negative 4.9t plus 24 is equal to 0. If you subtract 24 and divide by negative 4.9, you'll get t is equal to 24 over 4.9. Now let me just show you that on our graph. If I grab a calculator, which I'm just doing right now, you might be able to, if you listen closely, hear my clicks, divided by 4. This would be a great time for me to yell really loud into the microphone if you're listening closely. Then you find out that at time, this is 4.89, roughly 8. The height is going to be 8 again. I don't need to write the 8 there, but at that time. So again, that's roughly 4.898. Now, if you look at your equation, your function here, the lead coefficient is negative. So you happen to know that whatever parabola is connecting those 2 points, it's upside down. So it looks something like this. Well, probably more beautiful than that, honestly, but whatever. And if these 2 points are symmetrically placed at a height of 8, halfway between is the vertex. That should be natural. If you have a hanging chain like this and you know where these 2 points are, halfway between them is where the vertex will be. What's half of 4.898? Well, that's going to be 2.449. 2.449. Now that number should look very familiar because that's where our vertex was. Let me zoom out quite a bit here actually. But notice that is actually this right here. That's our vertex. But the way we arrived at that vertex is much more natural. It's when does our graph hit the y-axis? When is it at that height again? And then halfway between is where the vertex is. Let me say that again. So the first thing I think about is when does it hit the y-axis? Then I ask, when is it that height again? And finally I ask, or more so state, that halfway between those two is the vertex. Super nice, natural way of understanding that. You're more than welcome to steal that and use it. Or, since most students in this planet happen to do things with memorization, you could do the memorized negative b over 2a, but I really highly recommend trying to get a natural feel for it, because negative b over 2a is being memorized. You're going to forget that, but you'll never forget that a hanging chain will come back up to the same height later on and, down the road, and halfway between is the lowest point or the highest point. That is natural. You don't need math to understand that. You just need to know the world around you. Whereas the negative b over 2a, that's totally memorized. All right, that's enough for this video. I will see you in the next one.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry. Don't